So I've definitely started my recording this time. And if anything goes weird, I will try to reconfirm that it is still working.
Did you get your webcam working?
Yeah, I've got it off. I'm eating lunch right now, so you don't want to see that.
Alright, fair enough.
Yeah. But turn it on when I'm done eating. Alright, hope everybody's doing well. Go ahead and send me an attendance note. Let me know you're here right now. And any questions?
Yeah, I have a question about the homework.
Okay.
It's under chapter 3.3 and number 2, and I'm trying to find it on the text of what it is.
So 3.3, question 2.
Yeah. So it's asking about give an example of a proposition other than X that implies or that is implied by X. Can you kind of explain me how you get here?
Yeah, so part C?
Yeah, part C and then part D. I think I got part B down, but C and D are confusing to me.
So suppose I have a proposition A and B. All right, so suppose, let P be the proposition. A and B. So this is saying, find a Q such that P implies Q. So given the proposition that they've described X, right? Find a Q such that X implies Q. And there's always one easy answer. We know that X implies X. In other words, if X is true, then X is true. But that's not very interesting. But can you find a different proposition which, if X is true, that proposition Q is true? And so, for example, suppose P was the proposition A and B. Can we think of a proposition that is true if this is true?
If A is true, that implies A and B is true. Would that be a correct?
That's the right way of thinking about it, but we're looking for something that A and B implies. So we're looking for something here which is guaranteed to be true if this is true. And it's in what you just said, but you might have said it backwards.
Does it have to be guaranteed true? I thought the truth table for a single conditional could be false.
The question is asking for you to find something here which is guaranteed true if this is true. In other words, fill in the blank. If A and B, then blank. So that question, part C, is saying fill in the blank so that this statement is true. So how could we fill this in? If A and B, then...
So it could be A or B, right?
Yeah.
Or they both have to be true.
So if A and B, then A. So A is a proposition that's implied by A and B. B is also a proposition that's implied by A and B. A or B is a third proposition that's implied by A and B. Right? A or 2 plus 2 equals 11 is another proposition that's implied by A and B. So if we know this is true, there's a lot of other propositions we can write that we know are going to be true. Probably one of the simplest ones is just A. So part C is asking you to do that, but instead of, if this is true, if P and not Q, or R and P, that's the proposition that we're given, that's X. And so we're asked to show if X, then, so fill in the blank so that this statement is true. but it's the same idea as that. And then for part D, give an example of a proposition other than X that is implied by X. Oh, sorry, we just talked about part D. I had the questions wrong. So that was all for part D. Part C is saying give a proposition other than X that implies X. So part C is saying fill in the blank, if blank, then X. Part D is saying if X, then blank. Does that make sense?
Would it make sense to say if not X, then X?
Are you thinking for C?
Yeah.
Let's see. I don't think. Let's see. So if X is true, I don't think that's true, because if X is false, this is true, this would be false. So, let X be the proposition 1 equals 2. Well, if X is false, then 1 equals 2. Well, X is false, but 1 does not equal 2, so that's not quite right. And certainly if we said if X, then X, that would be true. But to say something other than that, we kind of need to look at what X is. And see if there's something that, if it's true, we know X will also be true.
So what if in the case, so I don't know if you want to go really deep into this question, but the only time on the truth table you get a 1 is when P is 1, but there's other cases where P is 1 but X is 0. So could you put if P then X, and most of the time it's true, sometimes it's not, or it has to be a guarantee?
It's got to be guaranteed.
So could you do like if P and not that this is an answer, but if P and not R then X, like would that be an acceptable proposition if it was true?
Something like that, yeah. If that makes it true, yep.
Okay. Okay.
All right, if you came in a little late and didn't do an attendance ping yet, send me a note. Let me know you're here. And we're talking about homework, and I'm eating my lunch.
When we get down to it, I have a question on 6. That's the last one I just had a problem with.
Which section?
This section. Yeah, that one there. So are we can't use any ors at all? It's only ands and negation?
You can only use ands and negation.
Okay.
Got any ideas?
Well, I started with P, not Q, and then not P, or and, not P, and Q. And then I thought about it and I said, okay, well, but if it's P and Q, then it's not going to work. And so then I was going to put and P and Q, but then that would mean everything would be 0.
Okay.
So you just kind of have to think about it a little differently.
Okay. When you're kicking around ideas, think about De Morgan.
I had a question about the Morgan's theorem.
Yeah.
A little bit. So, I was under the impression that you could basically take any conditional and apply De Morgan's theorem to it, right? And get the opposite.
Oh, logic?
Not maybe any condition, but certain kinds of propositions, yes.
Okay, so that confirms. Like, I found a condition and I tried to apply De Morgan's theorem to it, and I got a completely different conditional.
Mm-hmm.
So,
De Morgan's theorem really has two very specific forms, which are these two down here. And it's declaring the equivalence between this proposition and that proposition, and also an equivalence between that proposition and this proposition.
okay.
And yeah, we're still talking about homework.
That's just at the end of the section. I didn't quite gone that far.
Well, De Morgan's theorem, this table is page 58, which is the start of the next section. But
Okay.
but it's come up a few times in other contexts, including set theory.
Yeah, I think we used it on question 2B, right?
Very possibly.
You could use it there. Yeah.
Mm-hmm. Yeah, definitely. And we used it in an example of a proof last week where we stated a proposition and wanted to prove it. And we used identity, and we used De Morgan's theorem once or twice, and a few other things like that. So for quizzes and tests, somebody asked if we can have a note sheet with laws and whatnot. So we're remote, right, for fall. So my tests are open book. But I strongly recommend you make yourself a note sheet with just the stuff that you want on it. Now, page 58 and 59, really good things to have on your note sheets. And I usually hand these out to students in person and say you can use this in addition to your own notes, because you almost always want these written down, and you probably want these written down. But, you know, online you can use whatever you want from your textbook or your notes. You can't use online resources. But don't try to find answers in this textbook during a test. It's a recipe for spending a lot of time. Make some notes yourself with the stuff that you find relevant. And really, you know, one way to do school is you know, to take notes. And since the lectures are recorded, if there's lots of, you know, detailed stuff going on, you don't have to scribble it all down while it's happening. But it's still useful to try to write notes to yourself, right? The stuff that is the little ahas that go off, like, oh, De Morgan's theorem, right? Put a note down. And you can go back and expand on these notes later after class, possibly rewatching the videos and stuff. But the idea is that as you're going through a subject, you're building a set of notes for yourself, right? They're meaningful to nobody except you, but they kind of list the highlights. And then when you're working on homework problems, use your notes, right? As soon as you get to a new problem, don't start flipping through the pages of the book looking for an answer, right? That's how I did school. Don't be like me. Make note sheets. And by doing that, you know, you'll eventually discover, you know, I keep going back to this thing in my notes, right? That's a really important thing. Or I never look at this thing anymore. I know De Morgan's theorem now. I haven't looked at it in 3 weeks, right? You can take that off your note sheet. And then when you get to the exams are very much like homework questions. So the things you're doing in homework, that's basically what your exam questions will be like, right? The examples we go through in lecture, that's what your questions will be like. So if you've got a good set of notes that help you do your homework questions, those will also be helpful during your exams, usually. And it saves you from dealing with, you know, a few hundred pages of textbook, or, you know, 100 pages of notes from everything you've taken during the term. Not P and not Q equals P. Yep, good.
Okay, I didn't know if you wanted me to give that answer outside. That's why I sent it to you.
Yeah, I started reading it before I realized what it was. That's okay. I knew it wasn't personal, so. All right, cool. Any other questions? All right, so let's talk about quantifiers. So we're going to keep making new propositions from old propositions, and seeing where that gets us. So quantifiers are another way we can create new propositions from old. And there's two quantifiers we're going to work with. So one is written with an upside down A followed by an X. And this is called the universal quantifier. And it roughly means for all X. And the other is written as an upside down E followed by an X. And this is called the existential quantifier. It's not an upside down E, it's a flipped E. And it roughly translates to there exists an X. Alright, so for all X, or there exists an X.
So, for example, somewhere where you could use the existential quantifier would be like Rolle's theorem or squeeze theorem in calculus, where there exists a thing.
Yeah.
Okay.
But we won't go calculus in here. We'll do some simpler things. So there exists an X such that X is contained in the set of integers and X squared equals 4. That's not an and. And X squared equals 4. There exists an X such that X is an integer and its square is equal to 4. And this is a true proposition. If I said X equal to 2, that's an integer and its square is 4. Also, if I said X equal to negative 2, that's an integer and its square is 4. So this is definitely true. There does exist an X. But there exists an X such that X is an integer and X squared equals 2. That's false. Because there is no integer whose square is equal to 2. In fact, there's no rational number. There's no fraction of integers whose square is equal to 2. So that's a statement of this fact that the square root of 2 is irrational. But if I say there exists an X such that X is contained in the set of reals and X squared equals 2, that's a true statement. 1.4142 blah blah blah, right, is a real number and its square is equal to 2. It's called the square root of 2. So one thing to notice here is that the universe over which we're saying this X exists can be critical to the truth value of the proposition. Alright, I'm going to see if I can get my camera up. Well, it dissed my camera earlier and now I can't get it to come up, so that's the cookie. All right, so these are examples of existential quantifiers. Let me do one more that we'll play with a bit. Right, this is a fancy sounding way of writing the statement that negative integers are a thing. Right, there exists an x such that x is an integer and it's less than 0. Well, that's a true proposition. And it's stating that, you know, negative numbers exist, negative integers exist. Hey, it's a camera. All right, so that's the existential quantifier. The universal quantifier is the same idea. So let's see some examples for all x. X plus 1 is bigger than x. And I didn't say what the universe of x is, and sometimes we'll be a little sloppy and we may not explicitly list that. We should, but sometimes we'll get sloppy. But, you know, assuming x is a number, for all x, x plus 1 is bigger than x. Do we think that's true or false?
That's always going to be true, isn't it?
Yeah, that seems true. I mean, when you add 1 to something, it gets bigger. For all x, x squared is bigger than x. What about that?
That's false.
That's false. What's a counterexample?
If x was 1, it'd just be 1 is
Yeah.
bigger than 1.
If x is 1, 1 squared is not bigger than 1.
Or 0 would work too, I think.
Same with 0. How about for all x, x squared is bigger than or equal to x?
Think that'd be true?
That would be
Oh, no,
true.
it wouldn't be, because if x was
Because
negative,
negatives.
yeah, then it'd be 1 is... Or no, I guess it'd still be right.
Yeah, so if x is negative 1,
Cancel out the negative, so it'd always be greater.
yeah, x squared would still be greater. So for integers, this will always be true, but if x was 1/2, x squared would be a quarter, which is smaller than a half. So if x comes from the integers, this is true. If x comes from the reals, this would be false.
How would you put that in the notation there? So, like, if we want to say explicitly x is, I don't know, all natural numbers from 0 to infinity, no negative numbers.
So I would do this. I would say for all x contained in n. And you can also do that with the existential. I could say there exists an x contained in z such that. Remember, this colon means such that. So if it's not absolutely clear what the universe is, it's easiest sometimes to just list it next to the quantifier. There exists an x contained in z, or for all x contained in n, or something like that. And so the general format that we'll use these in is something like, for all x, p of x, or there exists an x such that p of x, where p of x is some proposition that somewhere in that proposition includes the variable x. So if I said, you know, let p of x be the proposition x squared is bigger than or equal to x. right? That's a family of propositions. P of 1 is the proposition that 1 squared is bigger than or equal to 1. P of negative 12 is the proposition that negative 12 squared is bigger than or equal to negative 12. So for any value of x, I have a corresponding proposition P of x. So it's kind of like a function, right? So this is saying for all x, let's say, contained in z, P of x is true. And we can say, is this proposition truthful or not? Is it true that for all x in z, x squared is bigger than or equal to x? Well, yeah, it is. We saw that. So it's interesting to try to negate some of these propositions. So suppose we have for all x, P of x. What would the negation of this be in terms of quantifiers and such? For all x, P of x is true. What's the opposite condition, the negative of this condition?
Wouldn't it be for all x the inverse P of x?
Possibly. So let's pick a proposition. So let P of x be the proposition. We're coming up on an election cycle. So P of x is the proposition that x went and voted today. So this says for all people, that person voted. In other words, this statement says everybody voted. So what's the negation of the sentence everybody voted? Is it everybody did not vote? Or is
Nobody
it?
voted?
Well, that's definitely an extreme situation, but is that the only possibility under which this statement is false?
Some people voted?
Some people voted.
Everybody.
At least one person did not vote. This says everyone voted. The negation of that is, hey, it's not true that everybody voted, which means at least one person did not vote, which means there exists at least one person such that P of x is false. So that's how we can negate a universal quantifier. It's the existential quantifier on the negation of P. But this is a weaker statement than saying for all x, not P of x, because that says nobody voted. And that could still be true if this is true, but this could be true even though, half the people did vote, which is usually what happens. All right, and in the other direction, there exists an x such that P of x. So this says at least one person voted. What's the negation of that?
Multiple people voted, or nobody voted at all?
Nobody voted at all. At least one person voted. If that fails to be true, what can we conclude? Nobody voted. Right? If anybody voted, then at least one person voted. So the negation of this is nobody voted. In other words, for all people x, not P of x. So we'll negate these sometimes. Like I said before, sometimes when we're trying to prove something, what we'll actually do is we'll assume the negation of what we're trying to prove, and we'll argue till we get to something ridiculous. And we'll say, if not P, then, 2 plus 2 equals 17. So P must be true, because if it's not true, we've got this ridiculous result. So we'll want to be able to take negations of propositions in different forms. So that's just something to keep in mind for quantifiers. Now these families of propositions, if we think of this as something like P of n, P parentheses n, we could define, a family of propositions where we have some wild card like n. So let's do an example. Let P of n be the proposition n plus 1 squared equals n squared plus 2n plus 1. All right, this is describing, and let me say, n is an integer. So I've just written an infinite number of propositions. So P of 0 is the proposition 0 plus 1 squared equals 0 squared plus 2 times 0 plus 1. P of 1 is the proposition 1 plus 1 squared equals 1 squared plus 2 times 1 plus 1. P of 15 is the proposition 15 plus 1 squared equals 15 squared plus 2 times 15 plus 1. For any integer n that I pick, P of n is a statement that has a truth value. And this is semantics, but they're really important semantics, because we're going to prove a lot of things about propositions written like this. And don't make the mistake of thinking that P of n is like a function that you plug n into and you get out this number, right? P of n is an English statement, or whatever language you write it in. It's a declarative statement that has a truth value. And we might say, prove P of n is true for all integers n. And so you're trying to prove that this infinite family of propositions is true. All right, so how does this relate to quantifiers? For all n contained in Z, P of n. This means P of 0 is true, P of 1 is true, P of 2 is true, P of negative 1 is true, P of 13 is true, P of negative 5,000,007 is true. So this is logically equivalent to the following. P0 and P1 and P2 and ... and P minus 1 and P minus 2 and ... This is a much easier thing to write than that.
Now, if you were going to prove this, obviously you wouldn't plug in 1, 2, 3 all the way up to infinity to prove it. Would you just try to get, like what we do in math, is do the algebra and try to get the left to equal the right? So you can say, in fact, it is true no matter what n you choose?
We could do that. So if we know the algebra, we could, apply some operations on this and show that this is equal to that. But we're not going to go that route. In effect, we're going to do that, but we're going to do it in a very, very different, much more formal way. We're going to work up towards something called mathematical induction. And we're not there yet, but we will get there probably next week. And it will be a very formal way of showing that all of these things are true.
So, I have a question for
Mm-hmm.
you. On the homework that's due Wednesday, there was a problem where we were asked to prove summations where n equals a specific number. So would that be like, is it different to prove for all n in all real numbers P of n, like you just did there, versus just prove P to the 0 equals the proposition quantity of 0 plus 1 squared equals 0 squared plus 2 times 0 plus 1.
Yeah,
Is it
so
different to just prove an individual versus the for all real numbers?
sure. Yeah, that homework question is asking you to look at a particular value and show, demonstrate that this is true, right? By using the definition of a summation and properties of commutativity and distribution of multiplication and so on. And you're basically proving, P of 3. I think it was for n equals 3. You're proving one particular proposition. And this is actually a really good lead-in to what we'll head to next week with induction. So let me pull that up, actually. Do you remember which section that was? I think it was chapter 1, right?
I think it was chapter 1.5.
Okay, yeah, it was the lingering chapter 1 question.
I think it was number 4 in that chapter.
Awesome.
Darn right there.
All right, so verify the following properties for n equals 3. So this is saying, set n equal to 3 and write out what this expression is, and write out what these expressions are, and show that, this left side and this right side are the same thing. So you'll add 3 terms together here, you'll add 3 terms here, 3 terms here, and you'll combine things and rearrange them and distribute some multiplication down here and so on, right? And it's an algebraic exercise. You have to sort of see how to do it, but once you see that, it's not that many steps to actually do. And we can do that for n equals 3. And if you try to do this for n equals 4, it's going to feel exactly like the same process, except you're going to have 4 terms over here, 4 terms, 4 terms. But that 4th term is not going to change what you did in the case with 3 terms. And then if you decided to do this for n equals 5, it's going to look exactly like the case for n equals 4. There's just 1 extra term. And if you were to do that for n equals 3, n equals 4, n equals 5, and then I said, do you think you could do that for n equals 6? You'd probably say, yeah, I'm pretty sure I could. And you would do exactly the same steps. And then if I said, could you do it for n equals 7? You'd say, yeah, definitely. How about 8? How about 9? How about 1,000,000? How about 1,000,000,000? Right? And you would be convinced at that point that you could do this for any positive integer n. But unless you actually do it for n equals 1,593,273,012, how do you know that it works for that n? Right? You have to actually do it. So this trick we're going to learn, mathematical induction, is a way to take what we would do ourselves to go from 3 to 4 to 5, and it will let us generalize it. And basically say, we can do exactly the same thing for any value of n. And it's a really powerful and really elegant technique. And we'll... Yeah, go ahead.
One more question. Last week, I couldn't remember because the video was cut off, but there was something we weren't supposed to do in terms of our proofs, and I think I solved this problem thinking that we're just proving this for n equals 3 and nothing else.
Mm-hmm.
It's okay to substitute it, but if we get something like that proposition we just had where the quantity of x plus 1 squared, see how you expanded it out to n squared plus 2n
Mm-hmm.
plus 1. If we tried to just substitute any random number in it when we're trying to prove p of n, that would be wrong. Right?
That would only prove it for the value of n you plugged in. So that would prove, if I plug n equals 17, that would prove p of 17. But that wouldn't generalize to all n. But the thing I said last week not to do is if you're trying to show something like this, don't start modifying both sides until you get to something that you see both sides are equal. That doesn't go back and prove this thing was true. So generally what we would do is we would take, for example, this left side, we could do something to show that this is the same as something else, and that's equal to something else, and that's equal to something else. And if eventually we show that, starting from this left side, we can show it's equal to this, then we're done. That's exactly what we're trying to prove. And we'll get through some specifics in a little bit that I think will make that clearer. But that was more of kind of a warning, just so that when we get to actually doing this, and I say don't do this, it'll be the second time we've seen it. That's all. Let's see, chat comments. So for all n in z, p of n basically means shorthand for plugging every integer within n into the function. It's a shorthand for plugging every n into the function and asserting that all of those resulting propositions are true. Right, so when we write this, the stating that this proposition is true means that this is true. And what if we go existential? There exists an n in z such that p of n Any idea what that might expand out to?
Would it be just like P0, P1, but instead of ands, ors?
Yeah, exactly. Because this is basically saying there's got to be some integer n for which p of n is true. It could be true for more than one. It could be true for all of them. But this quantifier states there exists at least one n for which this is true, which means either p of 0 is true, or p of 1, or p of 2, or, p of something, or, maybe p of negative 1, or p of negative 2, or, something like that. But it says that at least one of these has to be true. So just feeling wise, right? These quantifiers are related to other logical operations, conjunctions, disjunctions, and universal seems to relate to ands more, and existential seems to relate to ors more. And when we negate, we somehow switch from universal to existential and vice versa, and that's kind of De Morgan-ish, So there's some stuff going on here that might feel, like there's some consistency to what we've done in the past. But some of this intuition actually starts to break down at some point. So for example, for all x, p of x, and q of x. This says for all x, p of x is true and q of x is true. So for any x you think of, p is going to be true and q is going to be true. And so this is actually logically equivalent to the following. For all x, p of x, and for all x, q of x. And I think that makes sense kind of logically if you just sort of think about it in more common terms. Pick any x. This is saying both of these will be true. So let's say x is a set of integers, right? For any integer, p is true and q is true. Well, this says, for any integer, p is true, and this says for any integer, q is true. And if this is false, that's going to be false, and if this is false, that's going to be false. This says there exists an x such that p of x and q of x. That's actually not the same as this. So for example, let P of X be the proposition X is bigger than 0. Let Q of X be the proposition X is less than 0. Alright. Does there exist an X such that X is bigger than 0? True or false? There exists an X such that X is bigger than 0. That's true. We're working over integers. Alright, there exists an X such that X is less than 0. Is that true or false?
True.
That's true. So true and true, this is true. There exists an X such that X is bigger than 0 and X is less than 0. Is that true or false?
False.
Right? There's no integer that's both bigger and less than 0. So for at least, one pair of propositions P and Q, this side is false, this side is true. That's enough to say they're not logically equivalent. So we can play with these things all day, but you get the idea, hopefully, right? So two kinds of quantifiers. All right. Last thing we can do is nest quantifiers. And nesting always makes things interesting. So for all x, there exists a y such that x plus y equals 0. And we'll work over the integers again, right? So for all x, there exists a y such that x plus y equals 0. So I always put in parentheses, right? We can break it up like this. So this is saying, whatever x somebody hands me, can I find a y such that x plus y equals 0? So you hand me x equals 5. Is there a y such that 5 plus y equals 0?
Yes.
Okay, if you hand me an x of 3, is there a y such that 3 plus y equals 0?
Yes.
Right? Pretty much any x that you hand me, I can set y equal to negative x, and x plus y is going to be equal to 0. So for all x, there does in fact exist a y such that x plus y is equal to 0. So that's definitely true. How about if I switch the order around? There exists a y such that for all x, x plus y equals 0.
That would still be true, right? It would be the same statement.
So
I think it actually would be false because there isn't a y such that every x is equal to 0.
yeah, so any y that you think of, for example, suppose y equals 1. So this says, for all x, x plus 1 is equal to 0. Well, that's false. And if I let y equal to 0, this inner statement is basically saying for all x, x plus 0 equals 0. And that's false. And pretty much any value of y that you pick, you're going to find that this inner statement is not true. And so in fact, there does not exist a y which makes this inner statement true. And so this actually turns out to be false. And so our kind of intuition can break down with these things. And there's no sort of easy set of rules for, switching these things around or things like that. So you always want to kind of like think about these things on their own instead of deriving them from something else.
Can I ask you a question on that second?
Sure thing.
What if we set y to not x? Would that still do the same thing?
Well, this is not saying, this is saying there exists a y such that this is true. Right?
Y has
This,
to be an integer, it can't be a value.
yeah, we're not allowed to change it, right, based on x.
Okay. Alright.
So yeah, so there's an ordering to these basically.
So in that case, it would read y first, and it would x would have nothing to do with it until it gets into the condition.
Right, right.
Okay.
I'm sorry. Where exactly does the y equal 1 fit into an all x plus 1 equals 0?
So I was trying to sort of think through this, right? Suppose that this statement was true. It means that there is some value for y for which this inner statement is true. So I was just exploring, like, let's try some values of y and see if we happen to stumble across a value of y for which this is true. So I just arbitrarily said, suppose y is equal to 1. And we can quickly see that this inner statement is false. And if we pick y as 0, and so kind of a thought experiment will show you that no matter what value of y you pick, this statement's going to be false. And so this whole thing is going to be false.
Okay.
But if we said something like there exists a y such that for all x, x times y is equal to 0, that is true, right? The y which makes this true is y equals 0. And if I pick y equal to 0, this says for all x, x times 0 is equal to 0. Well, that's true. So we found a value of y which makes this true that satisfies the existential quantifier. While we're here, the other thing you'll see sometimes is an exclamation mark after E. So there exists P of X. This means unique. So this says there exists a unique X such that P of X. And normally when we say there exists, it could be 1, could be 2, could be an infinite number. But if there's only one thing that satisfies us, we say upside down E, exclamation mark, right? So that means there exists a unique.
So that would work for the one we just went through. Where there exists a y.
Yeah, so there does exist a unique y for which this is true. Exactly.
Okay.
All right, cool. Let's do like a 3 or 4 minute break, and then let's jump into rules of inference, which will be our main topic from here on out for the next few classes. Now let's do a 4 minute break. There you go. I'm going to turn off my microphone and eat my chips. All right, we're back. So rules of inference. So this is the real meat of propositional logic. Being able to write statements about inferences, conclusions we can draw from other facts, right? So what do we do in propositional logic? We construct propositions from other propositions, and in some cases we can assert that those propositions are true. And a lot of times the way we do this is by using the truth value of simpler propositions, or possibly more complex propositions. Oh, man. Oh, I just gave all the answers to the final exam and you missed it. Sorry. Yeah, thanks for the note. Okay, so, rules of inference. So, we're basically making new propositions from old propositions. And the idea of being able to prove things is sometimes, if we know the truth value of, a set of propositions, from those we can infer other propositions. And if we want to prove, X, and we can start with A, B, and C that we know are true, if we can somehow show that given A, B, and C, X is also true, then we can assert, X must be true because A, B, and C were true. So rules of inference are about how do we move from one proposition or a set of propositions to a new proposition. All right, so let me give you some examples. Let P be the proposition it is sunny. All right, and it does look sunny outside, so P seems to be a true proposition right now. Let Q be the proposition I go for a run. I'm not running much these days, but I want to get back to it because I miss it. So P is the proposition that it's sunny. Q is the proposition that I go for a run. All right. So here is a proposition derived from these. P arrow Q. If it is sunny, then I go for a run. Okay, that's a proposition. It has a truth value. P itself is another proposition. P is the proposition that it is sunny. Now, you don't know if this first proposition is true or false. Probably. You don't necessarily know if I go out and run when it's sunny. And if you're in a room with no windows, you don't know if P is true. And this could be a totally false proposition. This could be, if it's sunny, then I'm going to cancel class, which doesn't usually happen, right? And we might be having a night class and it might not be sunny out, right? So we don't necessarily know if this proposition is true or if this proposition is true. But nonetheless, we can make an absolutely true statement, which is if this proposition is true and this proposition is true, guaranteed Q is true. And this is the big gear change, right? This is where things start to happen. If this proposition is true and that proposition is true, you are guaranteed that Q is true. And that's a powerful statement. And it doesn't matter what P and Q are. They could be any wild proposition you dream up and scratch down on paper. But if this is true and this is true, you're guaranteed Q is true. And that's got a name. It's got a fancy name, which is modus ponens. But it's got a less fancy name, which is called direct reasoning. And if you go down to page 58 in your textbook, let me get there right now. It's also called detachment. And it basically says, given P arrow Q and given P, we can conclude Q. And there's a notational thing going on here. So there's this little double arrow instead of a single arrow. Double arrow is just a way to avoid parentheses, right? This thing that's written down here with this double arrow means exactly the same thing as this. But if I used a single arrow here, I got to have these parentheses around this statement. Otherwise, I don't know if this is P arrow Q implies P or P arrow Q implies P arrow Q and so on. So in the book, you'll see this double arrow to basically say, given all of this stuff on the left, if all of that, then this stuff on the right.
Isn't it called direct reasoning, though?
This is called direct reasoning or detachment or modus ponens, depending on who you're trying to impress. And in the homework that we'll post on Wednesday, I'll remind you what this double arrow means, right? It's this stuff on the left. If all of that, that's the hypothesis. This is the conclusion. All right, so we don't know if P implies Q is true. We don't know if P is true. All this is saying is if this is true and this is true, then Q is also true. And we'll write this like, an algebra equation. We'll write it like this. And when you see this kind of notation, it basically means if all this is true, then this is true. So it's a vertical way of writing, this horizontal thing, which we could also write with fewer parentheses by using a double arrow. So 3 different ways to say the same thing. All right, that's notational nuances. Let's talk about the heart of this, though. What does this actually mean? This statement says, if it is sunny, then I go for a run. This statement says it's sunny. This theorem is saying, if it's true that if it's sunny, I go for a run, and if it's true that it's sunny, then it's true that I'm going for a run. And that should make logical sense to us, right? If we really believe that if it's sunny, I go for a run, and if you look out and it's sunny, we're forced to conclude, hey, I'm going to go for a run. Why? Because this said it's sunny, and this said if it's sunny, I'm going to go for a run. Now, this statement might be false. Maybe if it's sunny, I'm going to go take a nap, right? But this theorem is still true. This theorem is always true. So given this and this, we can conclude that. Oh, sorry for the gym reminder. I was just commenting the other day, I missed the gym at Clark. All right, so that's one rule of inference, and it's called direct reasoning. And we can extend this. Suppose if A then B, and suppose if B then C, and suppose if C then D, and suppose A is true. Is there anything we can conclude from here?
Could we use direct reasoning is to say for detachment A, double A that special arrow sign equals arrow to D.
Yeah. So, I mean, if A is true, direct reasoning tells us that, since if A then B, we know that B is true. And if we know B is true and we know that B implies C, we know that C is true. Why? Direct reasoning. And now we know C is true, and if we're told C implies D, we can conclude D is true. And so this is a valid theorem. This is a valid statement of a conclusion from a set of hypotheses.
You could also basically just draw the A special arrow sign D, right?
So given these things, we can conclude D. But we could also say, if A implies B and B implies C and C implies D, well, those three statements tell us A implies D. Right? But if we said, A and A implies B, and B implies C, and C implies D, all of that would imply D. I mean, it also implies this, but D is an even more powerful statement than that. So this is very simple to show. It would probably take like 4 lines to prove this. Whereas if we did this with a truth table, we have 4 variables. We would have 16 rows in our truth table to fill out. And for each of those, we would have to fill out 5 columns. And that's a lot more work. And if we did this with 26 variables, right, we would have, 64 million rows in our truth table. Whereas we could do this with, 26 steps of a proof. So this is in a lot of ways more powerful, more usable for us than a truth table approach to proving statements, to proving propositions. All right, so let's look at another rule of inference. This is called modus tollens, or indirect reasoning. And it says the following. Suppose we're told that if P, then Q, and we're told not Q, we can conclude not P. And this is indirect reasoning. And the logic here is, if it's sunny, then I go for a run. I did not go for a run, therefore it can't be sunny. P must be false. And so all we're saying is if this is true and this is true, then that must be true. Does that make sense to everybody? Why this follows from that? So there's a number of these principles. So there's direct reasoning or detachment. There's indirect reasoning. There's disjunctive simplification. P implies P or Q. Well, what the heck does that mean? It means if P is true, then P or Q is true. What's Q? Does not matter. 1 + 1 = 2. 1 + 1 = 3. Doesn't make any difference. If you're told that P is true, you're guaranteed that P or Q is true. And remember, these things never say anything more than what they're saying. If P is false, this doesn't tell me anything. It doesn't tell me that P or Q is false. It doesn't tell me P or Q is true. This is only saying if P is true, then P or Q is true. This is only saying if these two things are true, then that's true. If this is not true, this doesn't tell me anything. If not Q is not true, this doesn't tell me anything. All right, we've got conjunctive simplification. P and Q implies P. So if you're told this, you can conclude P. And that's sort of you know, kind of what an and means. If we're told P and Q is true, well, then P itself must be true, right? If P was false, P and Q would have to be false. So if I tell you, you know, it's sunny and 1 + 1 = 2, you can conclude from that that it's sunny. You could also conclude from that 1 + 1 = 2. All right, disjunctive simplification. This is a funky one. So P or Q and not P implies Q. All right, if we know P or Q is true and we know not P is true, Q has got to be true. Put differently, this tells us that either P or Q must be true, possibly both. This tells us P is false. Well, if P is false and either P or Q has to be true, what do we conclude? Q must be true. Because if Q was false, P would be false and Q would be false, this would be false. Chain rule is what we were playing with here, right? If A then B, and if B then C, and if C then D, well, that means that if A then D. That's called a chain rule. And it's usually presented with just, you know, 2 levels of chaining. So if P implies Q and Q implies R, then P must imply R. And so there's a whole page of these. Conditional equivalence is something we can get from the truth table of an if-then statement, right? So if you look at your P, Q, and if P then Q, so the only time the conditional is false is when the hypothesis is true and the conclusion is false. Otherwise, this is true. Well, if you take this truth table and you throw it into a K-map, I said the word, and you do a simplification on it, what you'll find out is that this is the truth table for not P or Q. This has exactly the same truth table value as that. And so conditional equivalence is just a statement of that saying if P then Q is logically equivalent to saying not P or Q. They're the same truth value in all cases. And then if we put the arrow in both directions, P if and only if Q means if P then Q and if Q then P. And so if you replace each of these with the conditional equivalence, you get this kind of messy thing over here. It says P and Q or not P and not Q. And if you think back when we drew the truth table for this biconditional equivalence, what were the values in the truth table? 1, 0, 0, 1. Right? The biconditional was true exactly when P and Q had the same value, which is what this is saying over here. Either P and Q are both true, or not P and not Q are both true. In other words, P and Q are both false. And this is the last one in this table. This also comes from the truth table. If P then Q is the same as not Q. If not Q, then not P. And that's the good old contrapositive. All right, so let's just do a few more examples of this. So let P be the proposition it is sunny. Let Q be the proposition I go for a run. Let R be the proposition I take a nap. I don't know if I need all of these. Okay, so detachment. If it's sunny, then I go for a run. And it's sunny, therefore I go for a run. And we already said that makes sense. If it's sunny, then I go for a run. And I don't go for a run. Therefore, it's not sunny. And that's got to be logically correct. Because, you know, if it was sunny, and it's true that if it's sunny I go for a run, I would have gone for a run. And this would not be true. Alright, if it's sunny, then it's sunny or I take a nap. Right? And that's certainly going to be true. If it's sunny and I take a nap, then it's sunny. If it's sunny and I take a nap, then I take a nap. If I go for a run or I take a nap, and I don't go for a run, then I take a nap. Right? This is saying I'm either going to go for a run or take a nap. If you also know I don't go for a run, I must take a nap. If I'm going to go for a run or take a nap, and I don't take a nap, then I must go for a run. Because this is saying I'm doing one or the other. If it's sunny, then I go for a run. If I go for a run, then I take a nap. Therefore, if it's sunny, I'm going to take a nap. Well, I'm going to go for a run, and then because I went for a run, I'm going to take a nap. And then these just get a little weird. If it's sunny, then I go for a run. So either it's not sunny or I go for a run. And that, if you kind of think about it in that particular example, probably makes some sense. Right? So fix in your mind this idea, if it's sunny, then I go for a run. Right? So look outside, it's sunny, I'm going to go for a run. Right? So that's the same thing as saying either it's not sunny or I go for a run. And I'm not going to try to put words into this one or this one. Alright, does that make some sense? Alright, send me an attendance note. And we have no class on Friday, right? Friday's a day off. But Wednesday, I want to start developing proofs using this. So we'll start writing down some statements. We'll assign propositional variables for the different pieces of the statement. And then we'll start writing these kinds of equations to list what our statement is telling us. And we'll use these rules to try to develop other propositions that we can say are true. And we'll do some initial theorem proving using that. And then we're going to talk about fallacies, so variations on these that are absolutely not rules of inference, things that are not logically guaranteed to be true. And then we'll start digging into general techniques for proofs, direct proofs and indirect proofs. And we'll prove a bunch of things, and a lot of our proofs are going to come down to proofs about math, proofs about adding numbers together or taking square roots or things like that. But there'll be general principles we can apply in a lot of areas. All right, so come by office hours in the morning if you got questions on the homework. Otherwise, I will see you next time. Have a good one. And it's sunny out, so go run if you like running.
So, yeah, do you have time to,
I do not. I've got to get on to my next class.